Now let's discuss the actual way to represent documents and to match them with user queries if we talk about search and ranking. So first we will talk about retrieval that is based on terms or words. And these techniques, they match query words directly to document words. So if query word is different from a document word, even though they have the same meaning, for example, the matching will not happen. So this will be a precise matching between query words and document words, and the semantic matching where we will try to match meanings instead of specific words, we will discuss in the next set of videos. So we are starting to really talk about document representation and matching, and in this part we will talk about three main things used nowadays in IR. They have been used for many decades now, but they're still pretty effective, especially language modeling and BM25. So those are vector space model, where we represent documents as vectors, language modeling, where we represent documents as distributions, and then a very ad hoc method called BM25, and I'll talk about that a bit later. So vector space models. From the name, you can guess what it looks like. Maybe you've even seen that. So now we have the plays by Shakespeare here as documents. So we have 6 documents, and we have the vocabulary of those plays. Here we have 7 terms from the vocabulary. And whenever a term occurs in the document, we say it's 1. Whenever it doesn't occur, it's 0. So it's just binary occurrence of a term in a document. And then there's this matrix, and every document is a vector. And the same way you can represent the query. For example, if the query is, I don't know, Caesar and Brutus, then, and you drop, then the vector will be just 2 1s on these positions and 0s on all the other positions. How do you match 2 vectors? Well, clearly you just use cosine similarity, which is product between these 2 vectors, the vector for a document and the vector for a query, which if we put it into the sum of components, you go through all the terms in the vocabulary. V is the size of the vocabulary. We multiply the present, the entry for the document term, which is either 0 or 1, and the entry for the query term, which is again either 0 or 1. So actually for binary case, that goes down to just summing over the query terms, because everything that is not present in the query will not be in the sum. But clearly the simplifying assumption that the presence of a term is binary is it's too simple. What can we do better than that? Probably, actually, you've seen all this material in bachelor course. So this will be a bit of recap as well of IR0 and connecting it to IR1 as well. So what can we do instead of 0s and 1s? We can use term frequencies, which are just the counts of the number of times the term occurs in a document. So Anthony occurs 157 times in the play Anthony and Cleopatra, and it occurs just once in Macbeth. And that's it. So instead of 0s and 1s, we have term frequencies. But we can do, talking about term frequencies, we can use raw term frequency, just counting, or sometimes we want to smooth it a little bit because term frequency may be too aggressive, then we can use the log of term frequency. It's up to the application, and to decide which one to use, you need just to run evaluation with both of them and see what works better for your particular application, for your particular collection of documents. But the term frequency is not enough. It turned out somewhere, I don't remember exactly, probably 1970s. And people came up with this very, very smart thing that is super simple, but super effective. It's called inverse document frequency, or IDF. And it's the total number of documents in your collection divided by the number of documents that contain a term T. So that's why it's inverse. So this is document frequency, and this is the inverse document frequency. And again, to make it less aggressive, you take the log of it. And as an example, for example, you have different terms, and these are their document frequencies from 1 to 1 million. And clearly, the term that occurs in 1 million documents is not very representative. We want its IDF to be low. Instead, the term that occurs in very few documents like this too, we want them to really boost our weight. That's obvious, because if we search for the word the, well, it doesn't distinguish between documents really, while these two words do distinguish. So we want the weight for this to be higher. So IDF for those is 6 and 4, and IDF for the is 0 for this specific case, for example. So in the end, we have what is called TF-IDF, where we take TF, a term frequency of a word in a document, multiplied by inverse document frequency of the word. And this then is put into the vector representation. So we still have a vector, but each component of the vector is now TF-IDF. And again, term frequency can be raw or log, and document frequency, different works use also different formulas. It's up to you to decide which one to use, but standard is just TF and this version of IDF. These are standard. So in summary, in this first approach, though very simple, but you'll see how effective it can be when you build on top of it, documents and queries are represented as vectors, and they're matched using cosine similarity, obviously. Now, as for the weights of these vectors, you can use binary weights, not so effective. Term frequency is a bit more effective, but the most effective type of weight is TF-IDF.